Hi, this is Dr. Goldstein, and I'm going to talk about the derivatives of exponential and logarithmic functions. So let's start by discussing the derivative of the function f of x equals e to the x. And we are going to begin with the definition. So if we want to take the derivative of e to the x, we need to take the limit as h goes to 0 of f of x plus h minus f of x divided by h, which for this function means we're taking the limit as h goes to 0 of e to the x plus h minus e to the x divided by h. Now remember, when we have exponents that are added, we can break up the base by multiplying. So e to the x plus h we can break up as e to the x times e to the h, and then we have the rest of our limit. And then we can factor an e to the x out of both of the terms on the top there. So we have e to the x times e to the h minus 1 divided by h. And now the thing that we notice inside of this limit is this e to the h minus 1 divided by h. And if you remember from a previous video, we have a theorem that says that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. And this is because e is defined as the limit as h goes to 0 of 1 plus h to the 1 over h. So this theorem is a direct result of this definition of e. And if you don't remember how that works, go watch my previous video. So here, when we're taking this limit, the part that I've circled goes to 1, and so the entire limit goes to e to the x times 1, which is just e to the x. So what we've seen is that the derivative of e to the x is just e to the x. Nothing happens when we take the derivative. In other words, something does happen. We've taken the derivative. E to the x is its own derivative. It describes its own rate of change. And again, this is directly because of the definition of e, and this is why e is defined as it is. E is the special number that makes this true. So e is defined precisely so that this happens. Okay, so now that we know what the derivative of e to the x is, let's move on from there. So what if we wanted to take the derivative of e to the 3x? So we should think of this, if we have f of x equals e to the x, we should think of this as f of 3x. So this is e to the 3x. So we need to use the chain rule. In other words, this 3x is inside of this exponential function e to the x. So when we do this, remember the chain rule is that the derivative of some function f of g of x is f prime of g of x times g prime of x. Well, so the derivative of e to the whatever is just going to be e, and our g of x in this case is 3x. That's our inside function. So again, this is f prime of 3x. And now we have to multiply by the derivative of that, and so we multiply by 3, and that's our g prime of x. So we multiply this by 3. And so all in all, we get 3e to the 3x. Now, this example generalizes. So in general, the derivative of e to some constant k times x, you're always going to get this extra k as the derivative of this inside function, k times x. So the derivative of e to the kx is k e to the kx. And more generally, anytime we have e raised to some function, g of x, when you take the derivative of that, you don't change the exponential function. It is its own derivative, but because of the chain rule, we multiply by the derivative of that g of x. So this is what the chain rule looks like for exponential functions. This is the chain rule for e. Okay, we're going to use this in order to find the derivative of any exponential function, b to the x. So to start this, we want to write b to the x in terms of a base of e. And so we're going to write b to the x as e to the natural log of b raised to the x power. So again, remember, if we go in reverse, the e and the natural log cancel out. So e raised to the natural log of b is just b. And so overall, we end up getting e to the natural log b times x. And that natural log of b is a number. So when we go to take the derivative of b to the x, first we rewrite this as e to the natural log of b times x, and now we use the chain rule with e to the x. So we have this constant that is the natural log of b that comes out front, and then the exponential function is its own derivative. So again, we're using the chain rule. This is our g prime of x. That's the derivative for this g of x that's up in the exponent. Well, now, if I look at this expression, the e and the natural log are going to cancel out. So if we go to simplify this, I have the natural log of b. I have e to the natural log of b raised to the x power. Those cancel, and what I end up with is the natural log of b times b to the x. So overall, this is the derivative of b to the x. And again, this is another way of understanding why e is so special. So here, e is special because the natural log of e is 1, which again tells us that the derivative of e to the x is just e to the x. Okay, let's look at some more derivatives. We've defined derivatives of exponential functions for whatever base we want. Now let's look at derivatives of logarithms. And again, we have to approach this kind of sideways. So I'm going to write x as b raised to the log base b of x. So again, on the left-hand side of this, the b and the log base b cancel out, and I just get x. And so what I'm going to do with this is I'm going to take the derivative of both sides with respect to x. So I'm taking the derivative of both sides with respect to x. Now, on the right-hand side, this is simple. The derivative of x is just 1. But on the left-hand side, what I end up getting, I have b, which is a base, raised to the log base b of x. I can use the chain rule here, so this is my inside function g of x. When I take the derivative of a logarithm with base b, I get this extra natural log of b, and then the exponential function stays the same. It's its own derivative, b to the log base b of x, but then the chain rule tells me I have to multiply by the derivative of this g of x. But I don't know what it is. So I have to take its derivative just by writing, okay, take the derivative of this thing. So again, here in the chain rule, this is g prime of x. Okay, so altogether, the left-hand side of this derivative is the natural log of b times b to the log base b of x times the derivative of log base b of x, and the right-hand side is 1. Now, this derivative is what we want, so we're going to solve for this. We want to be able to take the derivatives of logarithmic functions. So I'm going to divide through by everything else. I'm going to divide through by natural log of b times b to the log base b x on both sides. So all in all, I end up getting, and these cancel out, I get that the derivative of log base b of x is 1 over the natural log of b times b to the log base b of x. Now again, remember back at the beginning, this b to the log base b of x was a silly way of just writing x. That b and the log base b cancel out. And so all in all, at the end of this, I get that the derivative of any logarithm base b is 1 over the natural log of b times x. So one thing that we notice here is that the derivative of the natural log of x, this is going to be 1 over the natural log of, the base of the natural log is e times x, but the natural log of e is just 1. So the derivative of a natural logarithm is just 1 over x. Let's see an example of this. Let's say that I want to take the derivative of the natural log of x squared plus 1. And remember, what we just concluded about taking derivatives of natural logarithms is that the derivative of the natural logarithm is just 1 over x. But here, we don't just have a natural logarithm, we have a function inside of a natural logarithm. So again, we have to use the chain rule. So this is going to be 1 over our g of x times g prime of x. And again, this is using the chain rule. So here, this expression, this is f prime of g of x, where f of x is the natural log of x, so f prime of x is 1 over x. This is kind of hard to see the first few times that you do this, but once you get used to it, it's not so bad. So all in all, when I plug everything in, I have 1 over my inside function, x squared plus 1, times the derivative of that. The derivative of x squared plus 1 is 2x. And so all in all, I have 2x divided by x squared plus 1. And that is my final answer. So that was a lot of derivative rules, and I am going to summarize them for you. So the derivative of b to the x for any base b is the natural log of your base times the exponential function b to the x. Now remember that the natural log of e is just 1, so for e to the x, that simplifies to e to the x. So this is why exponential functions with a base of e are so nice, because the derivative of e to the x is just e to the x. We also mentioned these two chain rules. They're very, very common, so they're worth writing down especially. The derivative of e to the kx is k e to the kx. Our inside function is k times x, and its derivative is k, so we're multiplying by the derivative of our inside function. And in general, if we have e to any function f of x, we have e to the f of x. So again, that is the derivative of e with the inside function plugged in, multiplied by the derivative of that. Okay, on the other hand, we have the derivatives of logarithms. The derivative of any logarithm log base b is 1 over the natural log of b times x. So in particular, if we have a log base e, meaning if we have the natural logarithm, we just get 1 over x. And what the chain rule looks like for logarithms, if our inside function is f of x, we end up getting 1 over f of x times the derivative of that inside function. And once you really get used to this, you'll just skip right to f prime of x divided by f of x. Okay, so there's a whole bunch of new derivative rules. Go find some problems to practice, and feel free to rewatch this video as many times as you like so that it makes sense.